from Friday. All right, so the question was asked again. Did y'all notice the little triangles on your unit circle?
I did.
Oh, I did that. That took a long time. Okay. So Dylan, you asked about the coordinates, and Katie, you asked about the tangent. So I'll go over both of those, and we'll make sure we can figure those out. All right. So if I'm in the first quadrant, well, the first quadrant has all those degrees there. That's okay. Yes, we do. That's how we learn. Boy, y'all are brutal this morning. Okay, here's my 45 degrees. That's right in the middle. And then below that, there's my 30. And then, everybody okay with converting those over to radians? Okay, those are not accurately drawn. Divide it by 180 and add a pi on it. Yeah. Not multiply it. All right, so we have pi over 6, pi over 4, and over 3. Divide by 180. So you can take out your calculator and you can do 30 divided by 180 and then hit math, enter. Get 1/6 the pi with it. Y'all good? All right, so the question was, first of all, how do I come up with these coordinates if I'm not a memorizer? So this is a 30, 60, 90 triangle, and the unit circle is special because the radius is always 1, right? So my hypotenuse on these triangles is always, right? So to go from hypotenuse to short leg on a 30, 60, 90 triangle, what? Divide by square, divide by 2, you're right, divide by 2, right? And then square root of 3. So it's I forgot to mute that. So this is square root of 3 over 2. So the coordinates there would be over the square root of 3 over 2 and up 1/2. I'm listening.
So it's x2 then? Wait, it's 36. Yeah. It's x2.
What do you mean? You talking about if you're setting up, you always start from the short leg, which is across from the smallest angle, which is the 30 degrees.
For the x coordinate, how do you get there? I need.
No, that's okay. You always take, so 30, 60, 90 triangle, if this is 30, okay, whatever the short leg is, okay, we called it x whenever we did it on Friday, but whatever you call it, you take the short leg and you multiply it by the square root of 3. You double it for the hypotenuse. So if you go backwards from either one of those, you have to divide instead of multiply.
And you end up, with 1/2 and you get that math.
Correct. Okay, so if you make it back, so if I start here, right, to get from here to here, I would need to divide by 2. Do you agree with that? So I take this radius, which this radius is always 1. I didn't say hypotenuse. You take this hypotenuse, which is always 1 because the radius is always 1. And I divide it by 2, and that's how I get the 1/2, right? Once I have the short leg of the special right triangle, it's easy to find the other sides because I just take the short leg and multiply by the square root of 3. So 1/2 times the square root of 3. So when I do fractions, I make into a fractional, so I put it over 1. And it's top times top and bottom times bottom. So I end up with the square root of 3 over 2 times 1 is 2. Other questions about that? Don't be a scared ass. For tangent. Okay. So for tangent, we said that's sine divided by cosine, right? And we did it with the whole triangle to show you, but if you just remember that it's sine over cosine. So if I do sine, remember cosine is the x, sine is the y. I always remember that because c comes before s, x comes before y. So cosine goes with x. Does that make sense? Okay. All right. So if I want to do tangent, I'm going to do sine over cosine. And since I'm dealing with fractions, really what I'm going to do is sine times the flip of cosine, because that's a little bit easier for me to work with, right? If dividing by a fraction is the same thing as multiplying by the reciprocal. Cosine is x and sine is y. Did you? I have never heard that. That's good though. All right, so what I'm going to do is I'm going to take sine, which is the y, right? So for the tangent, I'm going to take sine, which is 1/2, and I'm going to multiply it by the flip of cosine, 2 over square root of 3. All right, so here's where things get a little hairy. I have 2 over 2 times the square root of 3. Top times top, bottom. You can definitely cancel out the 2's. Ah, and it's 2. Thank you, Van. Thank you. All right. But then the problem is we have a radical in mind we have to rationalize. So in order to rationalize this, that is correct. All right, so 1 times square root of 3 is, what is the square root of 3 times the square root of 3?
3. Why is it 3?
Why is it 3?
I had like an epiphany on Friday. Why is it 3?
Okay, so 2 ways to think about this. Okay, square root of 3 times the square root of 3. Properties of radicals say that if you're multiplying and the radicand here is the same, this is the same, then I can combine what's under there together, right? As long as I'm multiplying or dividing. So this is the same thing as the square root of 9, which we know to be 3. The other way to look at it, which is the way that I prefer to look at it, is if I have the square root of 3 times the square root of 3, well, that's really the square root of 3 twice. These are opposite operations, and they cancel out, leaving with 3. Agreed. I like that way better, but whatever. But yeah. He told a story, didn't he?
Okay, I think I'm pretty good on like this. Not that we
Okay.
but it's just what is it like the radian values of the Pythagorean 5 like I remember that for the first quadrant and the next one.
Okay, so here's what I do whenever I look at it and I can't remember. The more you work with it, the more it'll just ingrain in your brain and you'll just know. This distance is always pi over 6 radians, right? It's also always 30 degrees, okay? Same here. So I need to take pi over 2, and to that I'm going to add the pi over 6 value, right? Because that's the width. That's this arc length here is pi over 6. Do you agree? That's, or the, not the arc length, but that's the degree there. Okay, so if I add pi over 6 to that, well, now I'm in a situation back pre-algebra or what, 8th grade math, where I have to have a common denominator to combine them. So common denominator here would be 6. So this would need a 3 and a 3. So I'd have 3 pi 6 plus pi over 6, which would be, which is
pi over 3.
Which is my first click there.
So yeah, so you're just adding that whole first part.
Yep. So each section is, this is pi over 6 degrees that are radians that I'm adding. This is not going to be, it's going to be, what is 15 divided by 180 is a fraction? Somebody do it.
5, 6. You said 150.
15 over 180.
It's 112.
No.
15 over 180.
What is 180 divided by 5?
112? 1/12. Is that what y'all are saying? Okay.
No.
So yes, so pi over 12. So I'm going to take this number and add pi over 12 to it. You see what I'm saying? You see where I'm going, how I'm deriving this as I go? Now, the other way to do it is, it's a lot of times, this is,
That would also be like in itself.
correct,
She's doing,
correct.
so there's 15 degrees.
Okay, but it may be easier for you. I've always filled in, if I didn't remember, filled in the degrees and then convert that over to radians. That's a little bit easier.
That would probably.
Okay.
I filled in all the degrees and I'm like kind of divided all
And that's exactly what I would do. Just remember, here's the only problem with that and why you get in a stuck point, it's a little bit easier. But I'm gonna show you some tricks. I'll show you this little video. Some people like it, some people don't. Most of these type questions are going to be non-calculator questions. So if you're using your calculator to go, oh, what's 120 divided by 180, math enter, to get, you see what I'm saying? You're not going to have a calculator to do that. Let me show you. You think that makes sense?
No.
Well, a lot of people.
That was that survey that she was quoting or whatever.
Yeah.
I got most of the discipline.
I didn't mean pause it. I just tried to make it.
You see, and in the second part of it, values that you need to know.
Hold on. Like it's the circle going around.
One finger and divide by 2. Just have the baby figure underneath.
This is the sign, remember. This is the sign.
Which signifies
Yes. All right, we're gonna pause it. No, pause, stop, wait. Oh, Stacy. What's the sign of 60? So if you go, sorry, y'all. Gotta rewind. We'll pause.
just have the baby figure underneath.
I'm sorry, I tried to pause.
One.
Let's be clear. Got it. And remember, if you can get the first quadrant, okay, we're back where we were before I paused.
Right by the answer.
Oh. No.
Yes.
It doesn't matter. That's okay.
0.
Yes.
It's 0. That's fine. finding close. Bend down the 5 times 60. Just 5 baseline finger above. Above, baseline below, same time. Every finger.
Square root of 1 over 3.
Did you guess?
What should be square root of 3 over 3?
Two angles, 245, 60. Because it's the
Some people love it. Some people love
I like
it.
it so like if I'm doing it,
Right.
because look, if you memorize it, you may forget it.
Memorize it, you may forget it. Okay, so. Right. You know, they change on you every now and then. All right, so I'm going to try to keep hitting you every day with some unit circle facts every day. Did everybody fill out your unit circle? Did you finish it? Just hold it up so I don't have to physically check that today. So I can give you all a 5 for your homework today. Yay, everybody. Okay, good job. All right. How are we feeling about the unit circle? Better than when you first had it in pre-calc?
Today and yesterday.
I like just learning.
Yeah, like I started school, like I haven't really done too much at like the very calculus, like we started going circles, she was like, start going over lit circles and lit. I was like, no, we started going over the unit circle calculus. She was like, I don't even know what that is.
What math is she taking?
Basic entry level college math, I don't know. But she had this place.
But she still had pre-cal. She should have had the unit circle.
Yeah, but she had
You're talking about confidence, right? In the circle.
Yeah.
More today than yesterday, but not as much as tomorrow.
Yeah. There you go, Noah. There you go.
I'm gonna wonder this. I did not.
What's the change in a pi over 4? It's an easy one.
I don't know.
The over 4s are the easiest because the coordinates are the same, so you only have to think about what quadrant you're in and if it's positive or negative, because when you divide by itself on tangent.
Okay, now I
See what I'm saying?
I didn't know. I was.
Um,
Are we allowed to look at it?
yeah.
I mean, the first one, homework, I did on the weekend.
How about the sine of 2 pi over 3?
Yeah, no, it's
Square root of 3 over 2.
Yeah. Are we gonna memorize to be able to do that?
So, yes. And I said, but as you go, the ones that pop up all the time, you'll start to see the pattern in them. These would, when they give you unit circle values, they're non-calculator questions. Usually multiple choice. Y'all ready to do some trig? Y'all need a brain break?
yeah.
Yeah.
Let's resume at 8:45.
We will go over transformations in just a second. I hope you guys remember transformations. Stretches, shrinks, ups, downs, reflects, all that kind of thing. If you add a number onto the end, it's a vertical shift. If you add, so we're going to talk, before we talk about the transformations, we're going to talk about the parent graphs, specifically the trig paragraphs, because that is where you all struggle, because for some reason we did not get to. If you need one, I will. I'm sorry. All right. What time is it? It's 8:45. I'm going to try to get through at least one basic, one co-function, and then one inverse. So I think I got 9 on here. Yeah, 9. And these are the ones that you really need to be familiar with because they're the ones that will show up over and over and over again, which is why you have a nice little packet. This took a while to make, but I think it looks nice.
You made it?
Yeah. It's impressive, right? Did it on Friday during my flaming. This should have come, you remember must know functions from pre-cal? You should have gotten to that because that's chapter 1. That's the end of chapter 1 in pre-cal.
We did. We did. So we didn't see it. Chapter 1. Yeah.
She was like, you should have learned this.
Wait, hold on. What? We might have gone to there.
Must know functions or basic functions,
Give me an
8
example.
parent functions.
Yes. She was later.
You talking about like the graph, like X
Quadratics. Yes, the parent function non-transform. Okay.
No, I wasn't. That's why.
Well, that's why I'm taking a little bit of time here to get it.
You do need those.
I know, right? So, okay, that's okay. We're going to go over the trig parent functions. Noah is trying to gain what, intelligence? What are you trying to gain?
Listen, my chakra thing, right?
Your what?
My chakra.
What's chakra?
Right?
Like, there's a head, a throat, and heart. Like, there's like hundreds of chakras. There's your third eye chakra. There's a nose, heart.
You're going to get a third eye.
The third eye is like intuition. It's like your pineal gland.
I got you.
Most people's pineal gland is our house gland. It sounds weird.
I think we'll just do some calculus now because I don't even understand what y'all are talking about anymore.
Put it in the air, the whole story.
Oh my gosh. I think y'all are misunderstanding the Christine. All right, sine. Let's do the sine graph. Here we go. Now, we're going back to reference that unit circle. Okay. So let's do some graphing here, and then we'll do some analyzing. I know y'all can analyze a graph because you had me for algebra 2, and we did a lot of graphical analysis. If y'all think back and remember. All right, so let's first graph it. Let me set my bounds on my y. What is the biggest value that sine ever has? 1. Are we all in agreement there? Yes. What is the smallest value? And what I'm going to do is on my graph, I'm going to graph it by half pies. Okay? So I'm going to start at 0. I'm going to say this is pi over 2. That's a half of pi, right? And then pi. I think yours goes by quarter pies, but the half pies are marked. Okay. 3 pi over 2. Well, it's labeled by half pies. There's a dash in the middle for the quarter pies. So, all right, I'm going to go opposite the same way. You don't have to, because this is already on your lovely sheet that I made you. Okay, so I definitely like found that graph and cut and pasted it there, but yeah. But I did make the table and everything. Now once I got one done, I mean it was just copy and paste, but you know what I'm saying? So, are there any places on the unit circle as you go around and around where sign is not defined?
Yes, at the Y.
Sign's not defined?
No.
Tangent. That's tangent, right? Okay, so there are no asymptotes because it's always defined. So where it says asymptotes, you can put none. How do we know if they're asymptotes?
Is there like nothing?
It's that invisible boundary that the graph never touches. It can't take on that value. In pre-cal, or I don't remember if we hit it at the end of Algebra 2, you learned about horizontal asymptotes when it's top heavy, bottom heavy, the same, or if you were dividing by 0, that gave you a vertical asymptote. So it's,
That's what I'm saying about like zero and like.
all right, let's start by finding some values. What is the sign? I'm thinking table of values in my head here, and I'm plugging in x values and finding what y is to go with it. So at 0, which is here, what is the sign of 0?
1. No.
So look at your unit circle because you really need
Pi
to.
over 6.
Whoa.
It's gotta be 0.
At 0, what is the y value?
0.
0, because sign is y, right? At 0. So this is saying the sign of 0 is 0. What is the sign of pi over 2? We're graphing, you don't have to write this, we're graphing, so I put 0, 0, because that's a point, right? Think XY chart if that helps you.
Oh wait, this one.
Yeah. Are y'all following me? Okay. Correct.
Oh.
So now what is the sign? Because this graph is the sine graph. What is the sign of pi?
So when you say sine of pi, you're saying what is the y of pi?
Yes. What is at pi? What is the y value? Sine of 3 pi over 2. I just have the gut instinctive feeling that y'all have not graphed this way for trig functions. You have? Okay.
Dylan was asleep when you
Okay.
very away for that explain.
Okay.
Like he did it on the board.
I think it's important for you to see the connection here and how it's, I
And
mean,
then you can just
But we
hold it
did
over.
this when I didn't know what the was.
okay, so that's probably why it was confusing. Okay, how about the sine of 2 pi?
You're up. Sine of every 2 pi.
Okay, so, and that's a good, that's great because you've got a place on here that says zeros. Where is the function 0? Right, so what values, let's finish graphing this, then we'll do it. Right. All right, so,
Which record would put 0 pi, 2 pi, and then like every
okay,
integer in pi.
we're going to do that too. We're going to do that. All right, so if you notice the pattern, 0 down, 0 up, 0, I mean, I know that's not mathematically, 0 down, 0 up, but here we go. I have this nice sine curve that we're going to do some analysis on. It is. You're absolutely right.
And we were just talking about wavelength.
That's right. It's a crystal, see?
That chocolate.
So if I throw this as much as I can into the board.
We'll call this amethyst. All right. Let's go through the analysis on it and see what happens. What's the domain? In other words, what all can x be? Left to right. So how do we say that? That is exactly right. How about the range? range is y, negative 1 to 1, inclusive, exclusive, inclusive, that's right, brackets. So my range, negative 1 to 1.
Okay, why don't we do the brackets?
Yep.
The brackets mean it's inclusive.
That's okay.
But the regular front, the parentheses, those are exclusive. So it doesn't matter.
Parentheses.
Yes, sir. You can't include.
No, the brackets are exactly.
Right.
Okay.
Y'all good? Even, odd, or neither. What does that mean? I hear even, neither. I hear both.
I think
Even odd.
she told us this.
Okay, I'm gonna tell you algebraically and graphically what it means. Okay. So algebraically, if you negate every x in the equation, okay. In other words, the sign of negative x. If it equals what you started with, then it's even. Okay. In other words, if you plug a negative in and every time you get sign of x back out, that tells me it's even. If you plug a negative in for every x and it makes the whole equation negative, that means it's odd. Okay.
Wait, can I write that down?
All right, so let's look at this one. Let's look at this one and see. Let's look at your unit circle again, okay? If I'm at, let's take an easy one. Let's say pi over 4. If I am at pi over 4, what is the sign of pi over 4? Okay, the sign of pi over 4 is the square root of 2 over 2. Are we all in agreement? If I make that x value negative, so what is the sign of negative pi over 4? What happens at, what does that mean, negative pi over 4? What does that mean?
When you're going like that in the graph, I was like,
I'm going backwards. That means instead of coming up here, I'm coming down here pi over 4 units. Okay, so what is the sign of negative pi over 4?
negative square root of 2.
Do you think that sign is even, odd, or neither? Odd. Because if it didn't give you the same or opposite, if it's just completely different. It could be a whole different number. It could be, when we look at algebraic equations, maybe we have something like x squared plus 2x minus 5 would be neither. If you plug negative in there, the middle sign would be opposite, but none of the other signs changed. And so it's not completely the same, but it's not completely opposite either. Yes. You can by just looking at the graph. So if it's reflective over the y-axis, it's even. So if it's symmetrical on both sides, think of a parabola. Okay, that's an even as long as it's centered at the origin. So if it's something like, nope. It doesn't have to be around 0, 0, but it does have to be, the vertex has to sit on that y-axis because that has an axis of symmetry of the y-axis. If that's the case, it's even. Okay, so then if you look, what did you notice about reflective properties on this one?
It's inverse.
Can it inverse? If what we say is it's reflective about the line. It's reflective about that diagonal line there.
You can
Y equals negative x, right. It rotates. If you take it and you go 180 degrees, it looks the same. That's odd symmetry.
So it's only even a parabola around.
No, that's not the only one. We're going to do one in just cosine. Cosine is actually an even
Or
function.
goes like absolute or
Absolute value.
And is that because
but if it's like that, is that
Yes. As long as it's on the y-axis, the vertex of it is. All right. We are going to spend an immense amount of time talking about continuity in here because we're going to redefine continuity every which way till tomorrow. Is this function, with you looking at it the way it is right now, is it continuous or discontinuous? Why?
Because you have the arrows.
Give me in layman's terms how you might, if you were explaining to someone in second grade how you could tell if a function was continuous.
Why you don't stop? You're explaining to a second grade. Because it doesn't have a break.
Okay.
Let's say
If you can draw it without lifting up your pencil, it's continuous. Okay, y'all think simple, think simple. Okay, so continuous. It does seem that way, doesn't it? But it's not. It's not. Oh yes. Just wait. I told y'all it's the algebra that sucks you, not the calculus.
I love calculus.
All right. We're definitely not getting as far as I thought today. I'm sorry. I talk too much. I just talk too much. But I just get excited. I like explaining it. Okay. I like seeing y'all make connections. Oh, I was going to say you haven't slept in here. Okay. Well, I appreciate that. All right. How about increasing intervals? What does that mean?
It's going up for those, but it's going down for those.
so it starts going up to 0.
So let's see. So from 0 to pi over 2, it's increasing.
From pi over 2 to.
How can I show that here?
Oh, we did this. Isn't there like a?
It's a U.
There's a U.
That means unity, right?
You could, in fact, what I'm going to do. Oh, yes. I'm sorry. We should. Let's do negative pi over 2 to pi over 2. And let's join with that. What? 3 pi over 2.
So why are these not inclusive?
What happens? We're going to talk about that now. We'll talk about where. Okay, so increasing means. I'm trying to think of how to explain it now without using calculus because we'll do this a lot with calculus.
Just an upward movement.
As you move left to right, is the function going up or going down? From these 2 points, for increasing, you look at where it's going up, where it looks like it has a positive slope.
You feel like every other integer pi, something like that?
Okay, so here we're going to go 3 pi over 2. Where does it stop increasing here?
And pi.
It is. All right, so this is 1 pi over 3, 3 pi over, 1 pi. What's the next unit? What's the next unit? There you go. Somebody said it. Everyone's a half of a pi, right? So half a pi, so I add 2 more. So it goes 1 pi over 2, 3 pi over 2, 5 pi over 2. So until I get to 5 pi over 2. And what I'm going to do now, until we get to the point where we're ready to do this, I'm just going to say u ... this way, and I'm going to say u ... this way. Everyone's a half a pi. So what is 2 pi plus a half a pi? What I do, I don't go that far. I mean, that's essentially what you're doing. But I look, every other one is a whole pi. So everyone in between is a half a pi, right? 1, 3, 5. Skip 1, what would the next one be? Skip one, the next one. And this would be 3 pi, 4 pi. All right, decreasing intervals. Same thing, but you're going with where it's going down. All right, so down. Okay, from, if I start at pi over 2, it decreases until I hit 3 pi. You can. And just hit at least 2 of the intervals and then do your dot, so you know that the pattern continues. Period. What does period mean?
I forgot. It sounds like a thing in learning chemistry, but like.
Oh, crap, it's 2 pi.
Why? What?
It's 2 pi because
It's the road.
that's like the, yeah, that's the full unit. Yeah.
How long before it starts repeating the pattern? Okay, how long it takes it to make a full cycle? Okay, so in other words, here, if I start at 0, it crosses back over at 0 here, but it's not doing the same thing. It goes up, down. Here, it starts repeating the pattern again, right? So it takes 2 pi to make a full circle. Well, that makes sense if you think about, I didn't mean a full circle, a full cycle. It makes sense because if you think about that unit circle, all the way around one time is 2 pi. And then everything repeats. Yes. When does the pattern start repeating itself? Start at 0 and see where it gets back to that point and starts, yeah. Is it? What does amplitude mean?
Like how high? Oh no, the amplitude is
I just think I remember the
it's like how long?
Okay, so yes. All right, so amplitude, what we do, we take, what? We take the max minus the min, okay? And I don't want to say just how high up on y it goes, because if we do that, it could be shifted up and that might throw you. So max minus min divided by 2. And I'll show you in just a second algebraically. Because it's the height of it from the y-axis if it's centered there.
Negative 1.
2 divided by, yeah. All right, so amplitude, we think of as being the height, okay? It's max minus min over 2. Highest minus lowest divided by 2. And we're definitely not getting to the shifts and shrinks and stuff today. I can see that. We said no asymptotes. All right, zeros, and then I'll move on to the little bit harder ones.
Wait, so the max is or negative 1.
1 minus negative 1. No.
1
Ah.
I didn't say
That's okay. That's fine. You got to see it, yeah.
Zeros mean where it hits at 0, right?
Okay, so zeros, and these are, y'all remember how critical these points were in Algebra 2. Zeros are where everything happens, right? All right, what are the zeros here?
There's 5 on this graph, but
There's 5 on this graph, but they have a pattern. So let's list them first and let's see what happens. There's a 0 at every, all right, so I got a 0 pi, 2 pi, right? 0, pi, 2 pi, dot, dot, dot. How could I say that?
Every other pi.
Every whole pi. So what I'm going to do is I'm going to throw a variable in there. We generally use k for whatever reason. So we say we have zeros at every k pi. Now here's where I'm going to use some little mathematical. I'm going to define k. So I'm going to say the zeros happen at every k pi, where k, this means is a member of, okay? That's like a funny looking E, yep. And then I do this little fancy Z for integers, okay? So this says that this graph crosses the x-axis at every k pi, where k, so every whole pi is where it crosses. 0 pi, 1 pi, 2 pi, 3 pi, negative 1 pi, negative 2 pi. That's what this is saying. Yes. This is member of integers.
Why are we talking about English now?
Come on,
All right, I'm going to leave you cosine and tangent to do. I want to flip over to secant.
All right.
Well, all right.
Maybe more. We'll
I
see what we
really
get
don't remember anything from speaking, coaching, and all that.
today.
It's like the inverse, it's gonna go up.
What is secant?
Secant is the opposite of sine.
1 over cosine.
1 over.
Okay, so remember this, and this comes up a lot. You have to remember it, especially when we start doing derivatives and integrals and stuff. You have to remember what secant means. Secant means 1 over cosine. What's cosecant?
1 over cosine.
1 over sine. What is cotangent? Give it to me another way. Cosine over sine for cotangent. If tangent is sine over cosine, then cotangent is cosine over sine. You just flip it. Okay? This is already going to give me some problems because I have something in the bottom, right? A cosine x, right? All right, so what I want to think about before I even start, and this is where I always start my cofunctions here. Well, it's not the inverse exactly. It's the reciprocal function. It's the flip. Where am I going to be 0? Because that's where my asymptotes are going to happen. So here's what I want to think. On my unit circle, again with the unit circle, you see we're going to use this so much, your brain's going to remember it. It doesn't have any choice but to, because you'll do it so much. Where is the cosine 0? Cosine is the what? The x. So where is x0 on your unit? Okay, so let's come up here. Cosine of x equals 0. Where? Where did we say? Pi over 2. 3 pi over 2. And we know because this is a unit circle and because this function begins to repeat itself, it's going to happen at all of these odd half pi's, right? So because this is where it's 0, I'm undefined at these points. Degree. That means I have asymptotes. So my asymptotes are happening, and I think this is on your sheet as well, or it should be. Yeah. But I need k to be odd. How can I define k to be odd here? That would actually probably suffice for most things that we're going to do here. You can. That's fine for right now. For right now, that's fine. For right now, that's fine. Just a variable. This is saying I have asymptotes because this is where the bottom is 0. Okay, so that sure is a member of. This is integers, yeah. So I'm looking at odd, yeah. All right, so let me just lay this out here. I've got pi over 2. I've got pi. We've got 3 pi over 2. Generally, we take these out to 2 pi. Why do we usually take these out to 2 pi? That's exactly right.
Why does this class goes by so much faster than others?
Because we have so much fun.
I really do enjoy it.
Thank you. I enjoy it too.
No, I'm gonna leave, so what should I do?
Maybe like
A shot? I don't really much of a shot. Oh, yeah.
We know those are asymptotes because those are where the denominator would equal 0. Right? Because I'm 1 over cosine. Secant is 1 over cosine. All right. Oh, dear. I have to figure some stuff out, right?
Oh,
so those are asymptotes. Well, it'll be discontinuous. Oh, so yeah.
There you go. And it's not continuous because it has asymptotes. I have to lift my pencil up to draw the whole thing, right?
Would that asymptotes not be on a...
But if I restrict that domain, I could be continuous, right? It is continuous on the domain negative pi over 2 to pi over 2, but it's not continuous on an infinite domain.
so the range is the negative domain.
No, your domain on this one. So you could write this 2 ways. You could say negative infinity to infinity where x cannot equal, so you can define what it can't be. So you could say negative infinity, infinity, but x cannot equal, and this is where k pi over 2, where k is an odd integer. Okay? Or we could say from negative pi over 2 to pi over 2, u pi over 2 to 3 pi over 2.
In order to do that, you have to.
Oh yeah, I forgot we hadn't graphed it yet. They were jumping ahead. I'm sorry.
Put 2 down.
Yeah, you need to. So you can pick up the pattern. All right, let's graph it. We should have graphed it before we did the. You can do either one. You can do it with union, or you can do it by defining k. Combine them. Yeah, kind of. All right. Let's graph it so we can look at the range. What is? Now remember, it's 1 over cosine, but what is the cosine of 0? The cosine of 0, so at 0, what's the x? 1, right? So 1 over 1 is 1. So here, I'm still at 1. Does that make sense? If I plugged in, no, 0, right? That means I want to know what is the secant of 0. So what is 1 over cosine of 0? Well, the cosine of 0 is 1. 1 over 1 is 1. All right, so I got 0, 1. Now, I don't have things marked on my graph in quarter pies, but if I did, what would happen at pi over 4? So if I'm kind of halfway between, okay, and I'm just looking at the square root of 2 over 2 is what everybody's saying, right? But because this is a reciprocal function, I need to flip that. All right, so if I'm at pi over 4, Is that bigger or smaller than 1? That's bigger than 1. Do we all agree? And in fact, do you agree that as you inch closer to pi over 2 here, those values are going to keep getting bigger? Would you agree with that? Because think about it, if I'm moving in closer on x, x is getting smaller, but then I'm flipping it over. So while x is getting smaller, because I'm moving closer this way, the reciprocal of x is getting bigger. So this is going to keep getting up bigger and bigger. It's a funky graph. Do y'all remember this graph? It is. It's like a bunch of parabolas. Yes, this is what secant looks like.
So it's
Yes,
always,
let's graph it 1.
but that's for every, so like the negative pi would be the same thing as parabola. Or you just do it.
Okay, no, it's going to flip. Because, okay, at pi, what is the cosine value? -1, right? So instead of it being up, it's going to be down here, and it's going to flip this way.
So what if it was at negative pi?
Same thing. So still all of these, because they are these periodic functions, they're going to start picking up the same pattern.
So if it's at top, it's going up.
Secant, cosecant's going to look just like this, only it's going to start out a little bit different, and it's going to be shifted. Okay, where did I lose you? Okay, so what is the cosine of pi? Yes. -1. Reciprocate it. So it's still -1. So the secant of pi is -1. 1 over cosine. So I just plotted the point pi, -1. They're going to hug those asymptotes on both sides. You don't. I just wanted to show you why. Because as you move closer and closer to this, your x is getting infinitely smaller until it gets to 0. So the reciprocal of infinitely smaller is infinitely bigger, which is why it goes up forever. So instead of approaching 0, it's approaching infinity. Huh? Yes. So here's the next piece. And so it continues this pattern.
Range the like to the values in the graph.
What is that value?
Other weird stuff that she just did with a K and a Z.
Well, you don't even have to. Bottoms up for range. So negative infinity up to, this is what stops it. What's that value? -1. But it includes it because there's actually a point there. And then it picks up where? At +1 up to infinity. I feel like y'all have not seen a secant graph before.
We have.
We ain't seen that.
It's great to me.
I have seen it, but pretend like
We would like to be treated like infants.
It's okay. Even, odd, or neither. It's even. It's definitely even, right? There is a line of symmetry on the y-axis for this graph. If you fold it over on the y-axis, it maps onto itself. Odd would be if you go and it maps back onto itself. It is discontinuous. It is infinitely discontinuous. Do you want me to show you mathematically? Okay. So for this one, if I do the secant of -x, yes, cool. 1 the cosine of negative x. Okay, so let's take a random value on here and let's see what happens. At the cosine, I like to use pi over 4. That's my favorite one to use because it's the easiest one to remember. It is always square root of 2 over 2. For both values, you just have to look at positive or negative, right? All right, so what is the cosine of pi over 4? Square root of 2 over 2. What is the cosine of negative pi over 4? Square root of 2 over 2. In fact, it doesn't matter if it's positive or negative on that. It's going to be the same thing, right? It's not going to change. So this is going to be equal to 1 over cosine x, which is secant x. So it stays exactly the same, which means it's an even function. Even, yes. That's fine. No, that's fine. What's the period? Yep.
No, it's the pi. It's every half pi. That's the period. No, because it's one of those. Sorry.
It's still 2 pi. Why is it still 2 pi? There's 2 of them. One's up and one's down, right? It takes 2 of them to make a complete cycle. Ooh, is the amplitude still 1? This one doesn't have an amplitude. It's max. Exactly. It's infinity. Yeah. Just don't worry putting on right there for that one. Yeah. I just copy and pasted. I shouldn't have. I'm sorry. No. So these are a little bit harder on your increasing. If you, for these functions, if you want to just label them on your graph instead of doing the intervals, I'm okay with that. There's a reason, and you'll see whenever we get there why I'm having you look to see when we're increasing, when we're decreasing. But if you want to come here and say that this is decreasing and this is increasing, and just label it on here and say, see graph, this is increasing, this is decreasing. No. No zeros, because it never crosses the x-axis, right? That's interesting. Just label it on your graph for these, because these get a little bit harder to.
So when we do for the asymptotes at every, like what would we write down?
I thought we wrote.
No, I mean we put them down. I'm just saying like under the